Farmingdale, New York. 16th of January, 1942. Republic Aviation's drafting room hummed with nervous energy as engineers studied performance charts for the P-47B. The numbers seemed impossible. 17,000 pounds at takeoff, ceiling above 40,000 feet, 8 50-caliber machine guns. In Europe, the air war favored nimble, lightweight fighters, the kind that could turn inside an enemy and win through agility. Yet here sat blueprints for a heavyweight, built not for dogfighting but for altitude, power, and raw survivability. Procurement officers from Wright Field expected resistance. They expected doubt. Instead, they found Alexander Kartveli's unwavering confidence in a design that defied convention. The Pratt and Whitney R-two-eight-hundred engine, coupled with a turbo-supercharger, promised speeds exceeding 420 miles per hour at 30,000 feet. As winter snow fell outside, no one yet understood that this overweight fighter would master the one dimension others feared most: the vertical dive. The heavy fighter nobody wanted was about to change everything. The factory floor at Farmingdale stretched under harsh industrial lighting, smelling of machine oil and fresh paint. Workers in coveralls moved between half-assembled fuselages, each frame larger and heavier than anything American fighter pilots had flown. The P-47B represented a gamble, not on speed alone, but on a fundamental reimagining of fighter combat. Where European designs chased maneuverability, Kartveli's team pursued something else entirely: the ability to convert altitude into velocity and velocity into survival. Test data from Wright Field arrived in thick manila folders. Early flights showed the prototype reaching 412 miles per hour at 29,800 feet. The turbo-supercharger worked. The R-two-eight-hundred engine, producing 2,000 horsepower on war emergency power, maintained manifold pressure well above 25,000 feet, an altitude where most piston engines gasped for air. 8 M2 Browning 50-caliber machine guns, mounted in the wings, delivered a combined burst mass of approximately 13 pounds per second. German fighters typically managed 6 to 8 pounds per second. The difference mattered. British Air Ministry liaison officers reviewed the specifications with polite skepticism. Weight was the enemy of dogfighting, they argued. The Spitfire succeeded because it could outturn its opponents. The Hurricane endured because pilots trusted its handling. This American heavyweight, at nearly double the Spitfire's empty weight, seemed a step backward. Yet the numbers told a different story. Structural tests revealed an airframe capable of withstanding dive speeds that would tear wings from lighter designs. Wind tunnel data suggested controllability would persist deeper into the transonic region than any contemporary fighter. The airplane wasn't built to turn with the enemy. It was built to dive through them, fire, and escape before they could respond. By late February 1942, the Army Air Forces accepted the design. Production contracts went to both Farmingdale and a new plant in Evansville, Indiana. The goal: equip fighter groups bound for Europe with an aircraft optimized for conditions American planners barely understood. In the month the P-47B proved viable, German fighter production showed the first signs of strain. Factories worked around the clock, but output lagged behind losses. The industrial imbalance that would magnify every American technical edge had already begun. Spring turned to summer. By April 1943, the first P-47 Thunderbolts arrived at bases in East Anglia. Ground crews at Halesworth and Hornchurch fitted long antenna masts and checked turbo-supercharger systems. Pilots fresh from stateside training climbed into cockpits and felt the weight, 7 tons at combat load. The airplane didn't feel nimble, felt solid, purposeful, like a truck with wings. Briefings emphasized altitude discipline. Stay high, maintain energy, avoid low-level turning engagements with Focke-Wulf 190s or Messerschmitt 109s. If an enemy climbed toward you, dive. If he followed, extend. Come back around with altitude in hand and repeat. The 56th Fighter Group, commanded by Lieutenant Colonel Hubert Zemke, flew early sweeps over occupied France and the Low Countries. Missions lasted 2 hours, pushing the Thunderbolt's internal fuel to its limit. Pilots learned to manage throttle settings, leaning the mixture to stretch range. Radio discipline improved. Controllers vectored sections toward enemy formations, and the Americans climbed, always climbed, seeking altitude advantage before contact. When German fighters appeared, typically between 18,000 and 24,000 feet, the P-47s held position above 28,000. The enemy climbed toward them. The Americans waited, watching fuel gauges and scanning the sky. Then, at the right moment, they rolled inverted and dove. Airspeed built rapidly. At 30,000 feet, the Thunderbolt accelerated from 280 miles per hour to over 450 in seconds. Gun sights tracked targets below. Pilots waited until range closed inside 300 yards, then pressed the trigger. 8 50 caliber guns converged, shredding wings and fuselages. The dive continued past 15,000 feet. Then pilots pulled back, recovered at 12,000, and used the R-two-eight-hundred's power to climb back to altitude. German pilots, caught in the dive's sudden violence, tried to follow. Their aircraft, lighter, more maneuverable at low speed, hit structural limits first. Elevator forces grew unmanageable. Ailerons froze. Pilots who pushed too hard found wings folding or control surfaces tearing away. The Thunderbolt, built heavy and strong, kept diving. 8th Air Force after-action reports from April and May 1943 noted a consistent pattern. P-47 pilots engaged, executed high-speed diving passes, and disengaged before opponents could force turning combat. Loss rates remained low. Experience accumulated. By June, the 56th Fighter Group had refined the tactic into doctrine. A Luftwaffe prisoner of war, debriefed after his capture, mentioned his squadron's inability to follow American fighters in vertical maneuvers without risk of structural damage. The gap wasn't just technical. It was tactical, rooted in design philosophy. One side built fighters to turn. The other built fighters to dive. In the sky over Europe, gravity favored the latter. Halesworth, 12th of June, 1943. The operations room smelled of cigarette smoke and stale coffee. Intelligence officers threaded gun camera film onto reels and projected footage onto a white wall. The images showed what words struggled to capture. Thunderbolts diving at angles exceeding 45 degrees. Tracers converging on enemy aircraft. Kills confirmed by debris and smoke trails. Most victories occurred in seconds, one pass, short burst, immediate extension. Turning engagements, when they happened, favored the enemy. But turning engagements had become rare. American pilots learned to refuse them. Zemke compiled observations into what became known informally as Zemke's rules. Maintain 5,000 to 8,000 feet altitude advantage over the enemy. Dive at 45 to 60 degrees. Open fire at less than 300 yards. Pull out above 12,000 to 15,000 feet, using the turbo-supercharger's power to regain altitude quickly. Never follow an enemy below 10,000 feet unless you have overwhelming numerical advantage. Never turn with a Focke-Wulf 190 or Messerschmitt 109 at low altitude. The rules weren't suggestions. They were survival protocols backed by math and blood. Group maintenance officers logged aircraft condition after each mission. Inspectors examined wing roots, control surfaces, and fuselage frames for stress cracks or rivet working. They found nothing. The P-47 tolerated repeated high-speed dives without structural degradation. Republic's engineers had built margins into the design that frontline use was only beginning to explore. Dive speeds regularly exceeded 480 miles per hour. Some pilots reported airspeed indicators touching 520, though instruments at those speeds were unreliable. What mattered was the recovery, and the Thunderbolt recovered every time with predictable control forces and manageable altitude loss. Controllers began logging a new metric: enemy engagement control. In 1940, over Britain, the Luftwaffe had chosen when and where to fight. By mid-1943, over France, that dynamic inverted. American fighters, operating at altitude with energy in hand, decided engagement timing. German pilots found themselves reacting, climbing, turning defensively.
Offensive initiative shifted.
The statistics reflected it. 8th Fighter Command loss rates declined while claims rose. The airplane dismissed as too heavy to dogfight was winning by refusing to dogfight. Instead, it used physics, potential energy converted to kinetic energy, mass multiplied by velocity, all focused through 850 caliber guns. The doctrine wasn't elegant. It was devastatingly effective. Boxstead, 23rd of August, 1943. The afternoon training cycle brought 4 ship sections diving on towed targets at staggered altitudes. Each pass pushed the aircraft harder. Steeper angles, higher entry speeds, tighter pullouts. Crew chiefs waited on the flight line with inspection checklists. When the Thunderbolts landed, mechanics swarmed them, measuring rivet working, checking for skin ripples or wrinkles, examining control surface hinges for play. They found nothing. Not a single rivet showed movement. Not one seam indicated stress beyond design limits. The expectation had been clear. Heavy fighters would suffer structural penalties in steep dives. Metal fatigues, airframes crack. But Republic's designers had anticipated loads others ignored. Riveted construction, thick wing skins, reinforced longerons. The P-47 was over-engineered by European standards, and that over-engineering paid dividends. Pilots learned they could dive the airplane repeatedly, day after day, mission after mission, without worrying about the wings coming off. That confidence, earned through inspection data and test flights, transformed tactics. Speed became life, and the Thunderbolt generated speed better than anything else in the sky. Training sorties averaged 1.8 hours. Pilots practiced dive entries, tracking, gunnery, and recovery techniques. They learned to read airspeed indicators at high Mach numbers, where instrument lag introduced errors. They practiced manifold pressure management, knowing that war emergency power settings could damage cylinders if held too long. Engine temperatures climbed during extended climbs, so they learned to monitor cylinder head temps and adjust mixture accordingly. Every system had limits, and those limits defined the tactical envelope. Inside that envelope, the P-47 dominated. Outside it, trouble waited. Squadron leaders documented lessons learned in after-action debriefs. One report noted that pilots maintaining altitude advantage before engagement survived at rates exceeding 95%. Another observed that German fighters rarely pursued diving P-47s below 18,000 feet, suggesting structural or tactical limitations. Intelligence officers compiled these observations into tactical bulletins distributed across 8th Fighter Command. The information flow worked both ways. Groups shared successful techniques, and headquarters synthesized them into doctrine. The training regimen intensified. New pilots arriving from the United States spent 2 weeks flying practice missions before their first combat sortie. Experienced flight leaders demonstrated proper dive angles, recovery altitudes, and energy management. Mock dogfights pitted sections against each other, with referees evaluating whether pilots maintained tactical discipline or allowed themselves to be drawn into low-altitude turning fights. Pilots who consistently violated altitude discipline received additional training. Those who mastered energy tactics moved to operational status. Maintenance logs showed availability rates in the low 70%. Good for a complex, turbo-supercharged fighter operating from muddy English fields. Spare parts flowed from depots. Engines were swapped in hours, not days. Propellers, damaged by ground debris, arrived as replacements before squadrons requested them. The logistics pipeline, still imperfect, improved weekly. Pilots noticed. An aircraft grounded today flew tomorrow. That reliability, multiplied across dozens of fighters, meant more sorties, more experience, more opportunities to refine the dive and extend tactic. In the same week, Luftwaffe units issued dive speed cautions. German pilots were warned not to exceed structural limits during pursuit. The Americans faced no such restriction. Their airframe was the limit, and the limit was very high. Wright Field, 7th of October, 1943. The wind tunnel hummed at near-continuous operation as engineers compared boost curves across altitude bands. Data from frontline units confirmed what test flights suggested. The R-two-eight-hundred engine, mated to the General Electric turbo-supercharger, maintained power output at altitudes where German engines faded. The Daimler-Benz 605 and BMW 801, used in the Messerschmitt 109 and Focke-Wulf 190 respectively, relied on mechanical supercharging. Those systems worked, but they bled power through drive losses and couldn't match the turbo's efficiency above 25,000 feet. Republic liaison engineers reviewed compressibility data. As aircraft approached the speed of sound, airflow over wings and control surfaces changed character. Shock waves formed. Lift distribution shifted. Control effectiveness degraded. Every fighter faced this wall, but they hit it at different speeds and with different consequences. The P-47, with its thick wing section and carefully designed airfoil, delayed compressibility onset longer than lighter designs. Test pilots reported controllability persisting past Mach 0.75 in dives, with elevator buffet serving as a clear warning before rail trouble began. Recovery was predictable. Reduce dive angle, accept altitude loss, wait for speed to bleed off, then pull smoothly. The procedure worked. Engineers debated adding dive brakes, split flaps or perforated panels to increase drag and control terminal velocity. Flight tests were conducted. Prototypes flew with experimental brake systems. Results showed marginal improvement. The airplane, as designed, already performed the mission. Adding complexity for minimal gain made no sense. The dive brake program was shelved. Pilots would manage speed through technique and discipline, not through additional hardware. That decision reflected confidence in both the airframe and the training. The P-47 didn't need help diving. It needed skilled pilots who understood energy management. Armament tests confirmed devastating firepower. 8 50-caliber Brownings, firing in convergence patterns set between 250 and 300 yards, delivered over 13 pounds of projectiles per second. Armor-piercing incendiary rounds punched through cockpit armor and engine blocks. German fighters, typically armed with two 20mm cannon and 2 rifle-caliber machine guns, fired heavier individual shells but at lower rates and with less total mass. The difference showed in combat. P-47 pilots described enemy aircraft disintegrating under sustained fire, wings shearing, fuselages breaking apart, fires erupting from fuel tanks. Ballistics experts calculated hit probability based on gun camera analysis. Short bursts from high closing speeds, fired within 300 yards, achieved kill rates above 30% per engagement. In aerial combat, where most bursts missed entirely, 30% was exceptional. The combination of 8 guns, high rate of fire, and concentrated convergence pattern made the Thunderbolt a uniquely destructive platform. German pilots, interviewed after capture, mentioned the psychological impact of facing American firepower. One described it as flying into a wall of tracers. Another noted that a single burst from 8 machine guns destroys any fighter. Technical officers at Wright Field also studied engine performance under combat conditions. The R-two-eight-hundred, originally rated at 2,000 horsepower, could deliver 2,300 horsepower on war emergency power for short periods. Pilots learned to use this boost during critical moments, climbing after a dive, extending away from pursuers, or accelerating to close on fleeing targets. The engine tolerated abuse that would have destroyed less robust designs. Cylinder head temperatures occasionally spiked above safe limits, but quick throttle management prevented damage. Oil consumption remained acceptable. Mechanical reliability, crucial for aircraft operating far from home bases, exceeded expectations. A proposed gun camera study analyzed hit percentages and confirmed what pilots reported. The weapon system worked. Abbeville and St. Omer, 9th through 22nd of November, 1943. Luftwaffe technical officers at Jägerschwader 26 conducted dive trials with operational aircraft. The goal: determine whether steeper, faster dives could counter the American tactic of diving to disengage. Pilots pushed Focke-Wulf 190s and Messerschmitt 109s into near-vertical descents, monitoring airspeed and control response. Results were sobering. At indicated speeds above 600 km per hour, elevator forces grew dangerously heavy. Aileron control degraded. Several aircraft experienced structural failures, wings crumpling, tail surfaces tearing away. Pilots who survived described the moment control disappeared. A sudden lightness in the stick, followed by catastrophic vibration. Unit diaries recorded the losses. Official guidance followed. Do not exceed safe dive limits below approximately 5,000 meters altitude. Maintain tactical discipline. Avoid deep pursuit of diving American fighters. The warnings were clear, but the tactical implications were profound. If German pilots couldn't follow P-47s into steep dives without risking structural failure, they lost the ability to force engagements. The Americans could attack, extend, and reset at will. The initiative belonged entirely to the side with altitude and structural margin. German engineers studied the problem. Test facilities at Rechlin examined captured P-47 components, seeking insights into American design philosophy. They found heavy-gauge aluminum in primary structure, extensive use of forgings rather than castings in critical joints, and wing spars dimensioned for loads far exceeding normal flight envelope. One German engineering report noted structural safety factors approximately 50% higher than comparable Reich designs. The conclusion was obvious. American fighters were built heavier because American industry could afford the weight. That industrial capacity, translated into stronger airframes, created tactical advantages no amount of pilot skill could overcome. Fighter tactics evolved in response. Luftwaffe units shifted emphasis back to bomber formations. If escorts couldn't be pinned down and destroyed, then focus on the mission objective, breaking up bomber streams before they reached targets. This meant head-on attacks against B-17 and B-24 formations, accepting high closure speeds and limited firing windows in exchange for disrupting formations before bomb runs. It worked, sometimes, but it exposed German fighters to mass defensive fire from bombers, 50 caliber guns in chin, waist, tail, and top turrets. Loss rates climbed. Experienced pilots, pulled from Eastern Front rotations or training commands, found themselves engaged in attrition warfare they couldn't win. Formation tactics changed as well. German fighters began operating in larger groups, swarms of 4 aircraft combining into formations of 12 or 16. The hope was that massed attacks, delivered simultaneously from multiple angles, could overwhelm escort defenses and reach bombers. Occasionally, the tactic succeeded. More often, P-47s at altitude dove into forming German groups, disrupting assembly before coordinated attacks could develop. Radio intercepts confirmed the problem. German controllers, vectoring units into position, complained of constant harassment during climb-out and inability to maintain formation integrity under vertical attack. Allied intelligence analyzed intercept patterns and captured German after-action reports. One document, translated from a downed pilot's notebook, included the phrase, "cannot compel horizontal engagement with Thunderbolt above 6,000 meters." Another mentioned, "dive escape successful regardless of initial advantage." The words confirmed what gun camera footage already showed. The tactic worked because the airframe enabled it, and the airframe enabled it because designers had prioritized strength and power over agility. The design philosophy, questioned by skeptics in 1942, stood validated by 1943 combat data. 8th Fighter Command analysis logged dive escape success rates above 90% when executed with altitude in hand. The airplane people called too heavy to dogfight had found a way to win without dogfighting. Ruhr approaches, 13th of December, 1943. Mission 85 targeted Bremen. Bombers droned eastward in combat box formations, stacked between 22,000 and 26,000 feet. Waist gunners scanned for fighters. Somewhere ahead, German controllers vectored intercept units into position. Then, high and to starboard, dots appeared, American escorts flying cover at 29,000 feet. The dots became identifiable. P-47s weaving in loose sections, watching the bomber stream and the sky beyond. German fighters formed up below, preparing attack runs. Standard procedure: climb to altitude, achieve position ahead of the bombers, then turn in for head-on or high-side passes. But before formations could complete assembly, the American escorts rolled and dove. Airspeed built instantly. Focke-Wulf 190s, climbing through 24,000 feet, suddenly faced P-47s in near-vertical dives, closing at combined speeds exceeding 600 miles per hour. The Americans fired, broke away, and extended before German pilots could react.
Formation scattered.
The bomber stream continued, unmolested. After-action reports from 1st Bomb Division crews used language like escort disrupted enemy assembly before contact. Loss rates, measured against late summer 1943, showed steady decline. Bombers still died, flak, structural failure, and determined attacks by fighters that broke through escort screens ensured casualties. But the trend favored the defenders. Each mission with P-47 top cover meant fewer concentrated attacks against bomber formations. Each disrupted intercept meant German pilots expended fuel and ammunition chasing escorts instead of engaging bombers. Bomber crews noticed the change. Tail gunners, who bore the brunt of attacks in previous months, reported fewer firing passes. Formation leaders observed German fighters breaking off earlier, climbing away to regroup rather than pressing attacks. Post-mission debriefs included comments like, "Escorts broke up the attack before they reached us," and saw P-47s diving through enemy formation. Scattered them completely. The psychological effect mattered as much as the tactical result. Bomber crews, knowing escorts flew above and could intervene, maintained tighter formations and executed bomb runs with greater precision. Mission effectiveness improved alongside reduced casualties. The Thunderbolts' combat radius remained limited. Without drop tanks, escort missions ended roughly 250 miles from base. Berlin, deep in eastern Germany, stayed out of range. But the Ruhr, Cologne, and targets in occupied France and Belgium fell within coverage. For those missions, escorts arrived, stayed, and fought on terms they controlled. Pilots learned to time their dives, coordinating with bomber streams to maximize disruption. German controllers, listening to radio chatter, adjusted tactics, but adjustments required fuel, time, and coordination that the diving attacks systematically denied. Statistical analysis from 8th Bomber Command showed the impact in numbers. During August 1943, before P-47 tactics fully matured, bomber loss rates averaged 6.3% per mission over defended targets. By December, with escorts executing refined dive-and-extend tactics, loss rates dropped to 3.8%. The reduction represented hundreds of aircraft and thousands of crew members who survived missions they might otherwise have died on. Mission planners incorporated the data into target selection. Deep penetrations remained costly, but targets within escort range became routine. The Thunderbolt, by controlling airspace above bomber formations, enabled the strategic bombing campaign to continue. One bomber pilot, interviewed after his 25th mission, described watching P-47s dive through an attacking formation. "They just fell on them," he said. "One second the Germans were climbing, setting up for their run. Next second, there's Thunderbolts coming down like hammers. The whole formation broke apart. We flew through without a scratch. The imagery was crude but accurate. The tactic relied on speed, surprise, and overwhelming firepower delivered in seconds. It worked because the airplane made it possible, and the airplane made it possible because engineers and pilots understood the weapon they'd built. Range remained a problem. The next model would change that. United States, 5th of January, 1944. Assembly lines at Farmingdale and Evansville ran 3 shifts. Workers riveted fuselages, installed engines, fitted wings, and painted national insignia. Finished airframes rolled off production lines onto flat cars bound for ports. Ships carried them to Britain. Within weeks of manufacture, P-47s arrived at depots, received final checks, and deployed to operational squadrons. Monthly production crested into 4 figures. The numbers, impossible by pre-war standards, reflected an industrial capacity no adversary could match. The P-47 D-20-5 model introduced a bubble canopy, replacing the earlier Razorback design. Visibility improved dramatically. Pilots could see behind and above without craning their necks. Mid-air collisions, a constant risk in crowded combat airspace, declined. Operational readiness, the percentage of assigned aircraft available for missions, stabilized in the low 70s. That meant a squadron with 28 assigned aircraft typically launched 20 missions with 18 to 21 flyable fighters. Maintenance crews worked miracles, swapping engines overnight, patching battle damage, and returning aircraft to service faster than peacetime standards permitted. Logistics officers tracked German fighter strength. Intelligence estimates placed Luftwaffe single-engine fighters defending the West at approximately 450 operational aircraft. American production delivered over 1,000 P-47s monthly. The math was unforgiving. Even with higher German sortie rates and superior pilot experience in some units, the numerical advantage favored the attackers. More aircraft meant more missions. More missions meant more opportunities to engage, learn, refine tactics, and press the campaign. Attrition affected both sides, but the side with factories running at full capacity replaced losses overnight. The sides stretched thin across multiple fronts struggled to keep squadrons at strength. Training pipelines expanded to match production. New pilot schools opened across the United States. Flight instructors, many of them combat veterans, rotated home after completing tours, taught energy management, gunnery, and formation discipline. Training emphasized the Thunderbolts' strengths: altitude performance, structural integrity, firepower, and downplayed its weaknesses. Dogfighting skills received less attention than dive bombing technique and deflection shooting. The curriculum reflected operational reality. Fights were won by pilots who controlled energy states, not by those who could execute the tightest turns. Drop tanks extended range. The 150-gallon jettisonable tank, hung beneath the fuselage, added crucial miles. Missions into central Germany became feasible. Pilots learned to manage fuel carefully, nursing the engine during cruise, shedding the tank when combat started, fighting on internal fuel, then calculating range to base with reserves for emergencies. The tactics remained unchanged. Climb high, maintain energy, dive when targets appeared, extend and reset. But now those tactics could reach targets that previously stayed beyond escort coverage. Ferry routes from the United States to Britain carried a steady stream of replacement aircraft. Depots in England received P-47s, performed final assembly, installed radios and gun sights, test flew systems, and delivered finished aircraft to squadrons within days. The logistics system, refined through trial and error, achieved efficiency that surprised even American planners. A factory worker in Indiana riveted a fuselage on Monday. By the following Monday, that aircraft sat on a flight line in East Anglia. The speed with which industry translated production into combat power shaped strategic calculations. German planners, tracking Allied aircraft numbers, watched the gap widen monthly. They couldn't match American output. They couldn't replace losses at equivalent rates. Industrial attrition, invisible in individual engagements, decided the campaign's trajectory. Production became a weapon. Each P-47 rolling off the line represented not just an aircraft but a tactical option. Another section that could fly, another pilot who could gain experience, another mission that could pressure German defenses. The factories worked with clinical efficiency, churning out airframes faster than frontline units could absorb them. Depots filled with reserves. Training units received new aircraft. Attrition, unavoidable in combat, barely dented available strength. With range kits and new models arriving weekly, Thunderbolts would soon escort bombers to Berlin. The heavy fighter that skeptics dismissed had become the backbone of daylight air operations over Europe. 19th of April, 1944, the Osnabrück-Munster Line. Ground controllers vectored 56th Fighter Group sections toward inbound threats. Bandits high, Wright 2 o'clock, Angels 2-8 pilots looked right, scanning the thin cirrus layer at 28,000 feet. Dots resolved into aircraft, approximately 30 Focke-Wulf 190s from Jägerschwader 54, climbing to intercept descending bomber formations. The P-47s held altitude, watching, waiting. Range closed. Then, on Zemke's call, sections rolled inverted and dove. The descent began at 29,000 feet. Within seconds, indicated airspeed passed 400 miles per hour. At 22,000 feet, pilots selected targets and pressed firing buttons. 850 caliber guns per aircraft erupted, converging fire raking across enemy formations. German pilots, caught mid-climb, broke defensively. Some tried to follow the diving Americans. Their aircraft, already near structural limits, shuddered and bucked as airspeed climbed. Several Focke-Wulfs shed pieces, cowlings, control surfaces, entire tail sections. The P-47s pulled out at 15,000 feet, regrouped, and climbed back to altitude on turbo power. The entire engagement lasted 90 seconds. Gun camera footage revealed the engagement's brutal efficiency. Frame-by-frame analysis showed tracers converging on German fighters, impacts visible as bright flashes against dark camouflage paint. One sequence captured a Focke-Wulf's wing folding upward at the root, the aircraft tumbling out of control. Another showed a pilot bailing out, parachute deploying against the clear sky. Intelligence officers counted exits. Of 30 German fighters engaged, 8 were confirmed destroyed, 6 probably destroyed, and 11 damaged. Not all claims would survive scrutiny. Overclaiming remained endemic, but the overall effect was undeniable. The German formation, intended to attack bombers, never reached them. After-action reports tallied results. Thunderbolts claimed 8 confirmed kills and probable damage to 6 more. American losses: none. One P-47 returned with minor flak damage to the tail section. The pilot flew it again the next day. The loss-exchange ratio, 8-0, represented the tactical ideal, destruction of the enemy without friendly casualties. Such ratios rarely occurred in air combat, but when they did, they validated doctrine completely. German pilots who survived the engagement described it in debriefs. One, captured after bailing out, called the attack impossible to counter. He explained that his squadron had trained for bomber interception, not for fighting escorts that dove from above at speeds his aircraft couldn't match. Another mentioned the psychological impact. You see them high above, then suddenly they are on you, firing, and gone before you can turn. The vertical attack, combined with overwhelming firepower and superior dive performance, left defenders with no effective response. They could climb, but climbing into diving attackers invited disaster. They could turn, but turning bled energy and allowed the P-47s to reset for another pass. They could dive away, but the Thunderbolt dove faster and farther. Every option favored the attacker. Combat analysis at 8th Fighter Command Headquarters reviewed the engagement in detail. The report, circulated to all fighter groups, highlighted exploitation of velocity exceeding enemy structural limit as the primary success factor. Pilots didn't outfly their opponents in traditional terms. They simply used the airplane's strengths, altitude performance, structural integrity, and firepower to create conditions where the enemy couldn't respond effectively. The engagement became a training case study. Other groups studied gun camera footage, analyzed attack profiles, and incorporated the lessons into their own operations. Flight leaders briefed sections on dive angles, firing ranges, and recovery altitudes using the Osnabrück engagement as the template. The 56th Fighter Group's best day demonstrated what the entire force could achieve with proper tactics and disciplined execution. The dive, once considered a maneuver of last resort, had become the foundation of American fighter doctrine over Europe. Tactical bulletins distributed across 8th Fighter Command reinforced the lessons. Maintain altitude advantage. Wait for the right moment. Dive decisively. Fire at close range. Extend immediately. Climb and reset. The doctrine was simple, repeatable, and effective. Pilots who followed it survived. Pilots who ignored it, chasing damaged enemies to low altitude, engaging in turning fights, or lingering in the target area, died. The statistics were unforgiving. The engagement over Osnabrück proved the doctrine worked not just in theory but in the chaos of actual combat against determined, experienced opponents. The tactic was no longer experimental. It was standard operating procedure. Eglin Field, 11th of May, 1944. The chase plane circled at a safe distance while the test P-47D pushed into a near-vertical dive. Instrumented recorders measured airspeed, altitude, and control inputs. The goal: determine the Thunderbolt's actual transonic limits, not through theory but through controlled flight test. As the dive steepened, the aircraft accelerated past 500 miles per hour indicated. The airframe shuddered slightly, compressibility buffet, expected and manageable. The pilot, a seasoned Army Air Forces test officer, held the dive, watching the altimeter unwind. At 8,000 feet, he initiated recovery, pulling back smoothly on the stick. Control forces increased but remained within acceptable limits. The aircraft leveled at 5,000 feet, having descended over 20,000 feet in less than 60 seconds. Post-flight analysis revealed impressive data. The P-47 maintained controllability deeper into the transonic region than any contemporary fighter. Mach numbers in excess of 0.8 were achievable before serious buffet or control degradation occurred. Recovery altitude loss, while significant, was predictable and repeatable. Pilots could push the dive, trust the airframe, and know they'd have sufficient altitude to pull out safely. Comparative data from German test facilities at Reckland showed earlier onset of control problems in both the Focke-Wulf 190 and Messerschmitt 109. The difference wasn't dramatic, perhaps 30 to 50 miles per hour in terminal dive speed, but in combat, that margin was decisive. Test engineers compiled detailed charts showing the relationship between entry altitude, dive angle, terminal velocity, and recovery altitude. The data allowed operational planners to calculate minimum safe altitudes for various tactical scenarios. A dive initiated at 30,000 feet, held to Mach 0.78, required approximately 12,000 feet for recovery. Pilots who initiated dives below 18,000 feet risked insufficient altitude for safe pullout. These numbers, derived from instrumented test flights, replaced guesswork with engineering certainty. Training programs incorporated the data. New pilots learned the limits before their first combat mission. Compressibility effects at high Mach numbers created unique handling characteristics. As airflow over the wing approached the speed of sound, shock waves formed, disrupting lift distribution. The aircraft's nose pitched down slightly, requiring forward stick pressure to maintain dive angle. Aileron effectiveness decreased, making lateral control more difficult. Elevator forces grew heavier as speed increased, demanding significant physical strength to initiate recovery. Experienced test pilots described the sensation. The airplane wants to keep diving. You have to fight it to pull out, yet throughout these effects, the P-47 remained controllable. The stick didn't lock. The elevators didn't freeze. Control remained possible, though it required technique and strength. Engineering memos recommended briefing frontline pilots on buffet onset and recovery technique. The message was straightforward. You can dive faster than the enemy, but know the signs of approaching trouble. Feel the stick shake. Watch the altimeter. Start recovery with altitude to spare. Don't get greedy. The guidelines formalized what experienced pilots already knew through trial and error. For newer pilots, the information was invaluable. It removed guesswork from the equation, replacing uncertainty with tested limits. Confidence grew. Pilots dove harder, knowing the airplane would hold together. Discussions about dive breaks resurfaced briefly and were dismissed again. The P-47 didn't need aerodynamic devices to control dive speed. It needed pilot discipline and understanding of the flight envelope. Adding complexity served no purpose. The aircraft, as delivered, performed the mission. Test reports circulated to operational commands, who incorporated findings into training syllabi. Squadron engineering officers received copies, using the data to advise pilots on proper technique. The near-transonic flight regime, barely understood at war's outset, had become routine for Thunderbolt pilots. Propeller-driven fighters were approaching speeds once thought impossible. The airplane itself, built with brute strength and excess power, had revealed capabilities its designers hadn't fully anticipated. The dive, practiced thousands of times over English training ranges and European battlefields, was now quantified, documented, and optimized. The tactic had become a science. Flight test data also confirmed the R-two-eight-hundred engine's exceptional high-altitude performance. Power output at 30,000 feet remained sufficient for rapid climbs after dive recoveries. While other piston engines struggled at altitude, the turbo-supercharged Pratt and Whitney maintained manifold pressure through mechanical ingenuity. The turbo compressed thin air, feeding the engine-dense, high-pressure mixture that generated horsepower comparable to sea-level conditions. This capability meant P-47 pilots could recover from dives, accelerate away from threats, and climb back to fighting altitude without prolonged vulnerability. The energy cycle, dive, attack, extend, climb, reset, depended entirely on engine performance at altitude. The R-two-eight-hundred delivered. Normandy and northern France, June through August 1944. The beachhead sprawled beneath broken clouds, crowded with ships, vehicles, and men pushing inland. Above, aircraft stacked in layers, transport planes, medium bombers, tactical reconnaissance, and at altitude, fighters. P-47s cycled between high cover and ground attack missions, dropping bombs on rail lines and strafing convoys, then climbing back to altitude to deter Luftwaffe interference. The pattern repeated daily. The sky over Overlord belonged to the Allies, maintained by overwhelming numbers and tactical superiority. German attempts to contest air superiority failed systematically. Luftwaffe units, pulled from training schools and Eastern Front rotations, scrambled to intercept Allied formations. They climbed, formed up, and approached the invasion zone, then encountered P-47s at altitude. The Americans dove, engaged, and broke up German formations before they could reach vulnerable targets below. Sorties fell sharply. Commanders on both sides tracked the numbers. By late June, Luftwaffe effectiveness over the beachhead had collapsed. Allied fighters owned the vertical, and owning the vertical meant controlling when, where, and how air combat occurred. Fighter direction reached new levels of sophistication. Ground-controlled intercept stations, equipped with radar, tracked both friendly and enemy aircraft. Controllers vectored P-47 sections toward threats with precision, giving altitude, heading, and estimated range. Pilots responded, climbing to position, waiting for optimal geometry, then diving when directed. The system reduced uncertainty. Fighters didn't waste fuel searching empty sky. They arrived where needed, when needed, with altitude advantage already secured. German pilots, lacking equivalent radar coverage and direction, operated at systematic disadvantage. They climbed blind, hoping to find targets, and instead found themselves targets. Statistical summaries from 8th and 9th Air Forces showed favorable loss exchange ratios. American fighters in the West achieved approximately 2.7 kills for every loss during the June-August period. The Thunderbolts' share of sorties remained high, and its combination of altitude performance, durability, and firepower contributed significantly to that ratio. Individual aces accumulated scores, pilots with 10, 15, 20 confirmed victories, but the aggregate effect mattered more than individual achievements. The Air Force was winning through systematic application of tactical advantages, not through individual heroics. German intelligence summaries, captured after the war, included phrasing like "American heavy fighters decide air battles in minutes," and "vertical attacks cannot be countered with current aircraft types." The admissions were buried in technical reports, but they confirmed Allied assessments. One document, translated from Luftwaffe Tactical Evaluation Branch, noted inability to force horizontal engagement above 6,000 meters, and consistent loss of tactical initiative to diving attacks. The language was clinical, but the message was clear. German fighters couldn't compel P-47s to fight on German terms. The Americans chose engagement conditions, and they chose conditions that favored their aircraft's strengths. Ground force movements benefited directly. With predictable air cover, supply convoys moved in daylight. Artillery positions operated without fear of sudden air attack. Infantry advances received close air support from fighter bombers that dominated the airspace. The Luftwaffe still flew. Aces still scored kills. But the overall calculus had shifted irreversibly. Allied forces could plan operations assuming air superiority. German forces planned operations assuming air harassment. That difference, rooted in fighter performance and tactics, shaped ground campaigns from D-Day forward. Tactical flexibility expanded as the campaign progressed. P-47s, originally conceived as high-altitude escorts, proved equally capable in ground attack roles. Pilots dropped bombs on bridges, strafed trains, and rocketed armored vehicles. The transition from air-to-air to air-to-ground and back occurred seamlessly. A section might escort bombers at altitude in the morning, strafe supply columns at noon, and intercept fighters in the afternoon. That versatility maximized the aircraft's utility, allowing commanders to allocate resources dynamically based on evolving needs. The Thunderbolt, too heavy to dogfight according to pre-war doctrine, had become the tool that made daylight operations viable. Altitude blocks and vectoring, enabled by radar and ground-controlled intercept systems, turned the airplane into a strategic asset. The dive ruled the sky because the sky belonged to whoever owned the high ground, and the P-47 owned the high ground by design. By late August, As Allied forces broke out from Normandy and raced across France, the air war's outcome was no longer in doubt. German fighter strength, bled by attrition and strangled by fuel shortages, declined weekly. American strength grew. The industrial and tactical advantages that skeptics questioned in 1942 had proven decisive by 1944. The airplane dismissed as too heavy had become indispensable. The tactic dismissed as defensive had become the war's most effective offensive tool. Gravity, harnessed through engineering and doctrine, had become a weapon. Army Air Force's Tactical Evaluation Branch, 12th of March, 1945. Washington, D.C. conference rooms filled with analysts, test pilots, and instructors compiling lessons from 3 years of European air combat. Charts covered walls, energy maneuverability plots showing climb rates, drag curves, and specific excess power across altitude bands. The data came from combat reports, gun camera footage, and engineering tests. One conclusion emerged clearly: altitude and energy management governed survival. Turn radius, the metric that dominated pre-war fighter design, mattered less than the ability to convert potential energy into kinetic energy and back again. Staff officers compared tactics across theaters. Pacific operations emphasized different requirements: long range, reliability over water, and flexibility for escort and ground attack roles. European operations validated the dive and extend doctrine. The analysts noted parallels. Successful fighter pilots, regardless of theater, understood energy. They climbed when possible, dove when advantageous, and avoided situations where low speed left them vulnerable. The principle transcended specific aircraft types. The Thunderbolts simply made the principle easier to execute by providing excess power, structural strength, and heavy armament. Post-war curricula took shape around these lessons. Training syllabi emphasized speed and altitude over turn performance. Instructors, many of them combat veterans, taught new pilots to think in 3 dimensions, not just left, right, up, down, but also fast, slow, and high-low. Energy states became core concepts. A pilot with altitude possessed potential energy. A pilot in a dive converted that potential into kinetic energy. Managing the conversion, knowing when to dive, when to extend, when to climb, separated survivors from casualties. The P-47's combat record demonstrated the doctrine's effectiveness. It also provided quantitative data that engineers used to design the next generation of fighters. Captured German technical documents acknowledged American disengagement tactics. One Luftwaffe evaluation, dated February 1945, included language praising the effective use of altitude and dive speed to control engagement timing. The report recommended German fighters adopt similar tactics, but noted that existing aircraft lacked the structural margins and power required. The admission arrived too late to matter, but it confirmed what Allied pilots knew. The tactic worked because the airplane enabled it. Doctrine followed design. The heavy fighter, dismissed as a dogfighting liability, succeeded by refusing to dogfight. Instead, it fought on its terms, using physics and industrial capacity to impose outcomes the enemy couldn't prevent. Analysis extended beyond tactics to industrial implications. The United States produced 15,683 P-47s during the war. Germany produced approximately 33,000 Messerschmitt 109s and 19,000 Focke-Wulf 190s combined across all variants and years. The raw numbers suggested German superiority, but operational reality told a different story. American fighters arrived in theater within weeks of manufacture. German fighters, strangled by fuel shortages and spare parts bottlenecks, sat grounded despite nominal availability. Industrial capacity meant nothing without logistics to support it. The United States built airplanes and the infrastructure to sustain them. Germany built airplanes and watched them become unflyable for lack of fuel and parts. By the time jet aircraft entered service, energy management doctrine was already codified. The transition from propeller to jet changed speeds and altitudes, but the fundamental principle, control the vertical, control the fight, endured. What saved Thunderbolt pilots in 1943 became the foundation for jet-age tactics. The heavy fighter earned its legacy not through agility, but through something more valuable: bringing pilots home. Europe, 8th of May, 1945, V-Day. Squadron operations boards across Britain and the continent tallied final counts. Adjutants closed war diaries. Maintenance chiefs logged aircraft status for the last time as combat units. Ground crews, exhausted and relieved, gathered around aircraft they'd serviced for years. Pilots, some with 50 missions, others with 100+, stood beside their P-47s and reflected on survival. The airplanes, battered and patched, represented more than machines. They represented a design philosophy that prioritized strength, power, and survivability over elegance and agility. Final production numbers told one story: 15,683 P-47 Thunderbolts built across all variants. Combat records told another: thousands of aerial victories credited to Thunderbolt pilots across theaters. The exact number remained debatable. Overclaiming occurred in the fog of combat, and multiple pilots sometimes engaged the same target, but the aggregate effect was undeniable. American fighter groups equipped with P-47s achieved air superiority over Europe, providing bomber escort, disrupting enemy operations, and enabling daylight strategic bombing. The airplane, too heavy by conventional wisdom, succeeded because conventional wisdom missed the point. Pilot survival rates exceeded expectations. The P-47's rugged construction absorbed battle damage that would have downed lighter aircraft. Pilots returned from missions with shot-up airframes, damaged engines, and shredded control surfaces. Mechanics repaired them overnight. The airplane's structural integrity meant pilots could press attacks, absorb defensive fire, and still make it home. Loss rates, while never negligible, remained lower than projections. Combat attrition claimed aircraft and pilots, but the survival-to-loss ratio favored the Thunderbolt. That ratio mattered. Experienced pilots stayed alive longer, accumulated more missions, and trained newer squadron mates. The cycle reinforced itself. No documented structural write-offs occurred from correctly executed dive recoveries in frontline units. That statistic, buried in maintenance logs and engineering summaries, validated the design's core strength. Pilots dove the airplane hard, repeatedly, for years, and the airframe held. Rivets stayed tight. Longerons didn't crack. Wings didn't fold. The margins engineers built into the structure proved sufficient for the most demanding operational use. German post-war interviews, conducted by Allied intelligence teams, noted the Luftwaffe's inability to compel sustained horizontal engagements against P-47s at altitude. The admission lacked drama but carried weight. One side built fighters optimized for turning combat. The other built fighters optimized for energy management. Over Europe, energy management won. The Thunderbolt's tactical legacy extended beyond numbers. It demonstrated that industrial capacity, translated into reliable, powerful, and heavily armed aircraft, could shape strategic outcomes. It showed that doctrine must follow design, not the other way around. Most importantly, it proved that survival and lethality weren't mutually exclusive. An aircraft could be both deadly and survivable if engineers prioritized the right characteristics. By war's end, P-47s still flew missions using the same boom and zoom method developed in 1943. The tactic hadn't changed because it didn't need to change. The numbers, kill-to-loss ratios, mission success rates, pilot survival percentages, favored it from the start. A fighter dismissed as too heavy to dogfight used gravity, horsepower, and overwhelming firepower to dominate the air war. The lesson resonated through subsequent decades of fighter design. The dive, once considered a desperation maneuver, had become the weapon. And the weapon had been decisive. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.